In this video, I'm going to go over solving a linear programming problem that has context wrapped around it. So we're going to need to set up our objective function, set up our constraints, graph our constraints, figure out the values at the corners, and then decide which one of them gives us what we desire. So going through all of that, here our situation is that food and clothing are being shipped to victims of a natural disaster. Each carton of food will feed 11 people, while each carton of clothing will help 4 people. And then they give us some constraints or limitations on the weight of these cartons as well as the size of the cartons. Then what we're asked to find is how many cartons of food and clothing should be sent with each shipment to maximize the number of people helped. And so here our objective is to maximize the number of people helped. And so that means when we set up our objective function, what we're trying to figure out is how many people are we going to help. So it means we'll set the z of our objective function to be the number of people helped. Now what we're actually looking for is how many cartons of food and clothing. Okay, so that will be our other two variables, are the number of cartons of food and the number of cartons of clothing. Alright, so that gives us z is the objective, which is to maximize the number of people helped, and then x and y are what we have control over to reach that objective. In this scenario, it's number of cartons of food and number of cartons of clothing. Alright, so now that we have that, we need to use those variables to set up our objective function. Well, that's where we go back to the problem and read how number of people helped relates to the number of cartons and the number of food. I'm sorry, the number of cartons of food and the number of cartons of clothing. So in the problem we have that each carton of food will feed 11 people and each carton of clothing will help feed 4 people. So that means that the number of people helped, z, is given by 11 times x, because 11 people for x cartons of food, plus 4 times y, or 4 people for each carton of food, of clothing y. So that's our objective function. And that's how we're going to test out how we maximize stuff. Now what we need to do is set up our constraints. And our constraints are basically based on pounds and pounds of that we're going to pack in the carton. The total weight can be 24,000 pounds. And the size, or the cubic feet, it has a maximum of 8,000 cubic feet. So to organize this information that's given in the problem, I'm just going to set up a quick chart. Okay, so we have food, and this is just to help me organize information, and clothing, and then we've got the weight, and we have the size. Just a quick little chart. So then we need to read in the sentence here, let me erase this. Each 20 cubic foot of food weighs 40 pounds. Alright, so when we're dealing with food, it's 20 cubic feet that weighs 40 pounds. Alright, and then the next one on that is each 5 cubic foot of clothing weighs 20 pounds. So then for that, the size would be 5 cubic foot per container, or per box, and then that weighs 20 pounds. Okay? So those are that just helps me organize that information and get it out of a sentence and in an easily accessible way. So then the other thing I'm going to use for that are these sentences here and put all that together. Let me erase some of this highlighting though. So as far as my weights go, it cannot exceed 24,000 pounds. And here are my weight measurements. Now remember, food corresponds to X and clothing corresponds to Y. So when I put all that together, what I'm going to get is that the number of cartons I have of food times 40 that would be the weight of all the food, plus the number of cartons of clothing I have times 20, that would be 20y, that would be the weight of all the clothing. That cannot exceed 24,000 pounds. And so that is one of my constraints. Now my other constraint here is going to be based on volume, and my volume is that each carton has a volume of 20 cubic foot each one of food. So that would be 20x would be my total volume of food, and then 5y would be my total volume of clothing, and then that cannot exceed 8,000 cubic feet. Okay, so those are my two constraints, plus the idea that we can't have less than 0 cartons of food and less than 0 cartons of clothing. So 0 bounds the minimum side of that. Okay, so now that we have all of that, what I want to do is graph my constraints to kind of figure out where my corners are, or my vertices, to get a sense of where my potential maximums are. I'm going to get rid of this chart to make room for the graph, because the chart was just to help me organize information so I could come up with the constraints. Now that I have the constraints, I don't really need the chart anymore. So I'm going to draw a graph in here. And this graph it doesn't have to be perfect. The idea is to give you a sense of where the corners are. Okay, so to graph this, because of these crazy numbers on the constraints, what I'm going to do is find the x and y intercept for each of those lines. So to find the x-intercept, so we'll just work on graphing this first constraint first. To find the x-intercept, I plug a 0 in for y. Doing that zeroes out my y term, and so to solve for x, I just need to divide both sides by 40. When I do that, I'm going to get that x equals 600. So in other words, my x-intercept is the order pair 600, 0. I'm just writing that there for now. But what I want to do on my graph is I'm going to count by 100. So this is 100, 200, 300, 400, 500, 600. There's my x-intercept for this constraint. And I'm going to go ahead and label it 600, 0. And then I won't have to keep this over here. I'll just store it on the graph. Okay? Now we're going to what we're going to do is switch gears and find the y-intercept for this same constraint. Alright, to find my y-intercept, I'll plug a 0 in for x, which basically just zeroes out my x term, which means to solve for y, I need to divide both sides by 20. When I do that, I get 1200, so my y-intercept is going to be 0, 1200. Okay, so putting that on the graph, again I'm going to count by hundreds, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I'm going to go ahead and extend this up. Just pretend like those words aren't there. 12. Okay, and then that's going to be my y-intercept, and so I draw in my constraint line here. And remember, the x and y axis are also constraint lines because we can't have less than 0 cartons of anything, and so we kind of have that triangle there so far. Okay, now we're going to switch gears and work on graphing the other constraint equation. So again, I'll just find my x and y intercepts. To find my x-intercept on this constraint equation, I'll zero out the y term and then divide by 20. That's going to give me a 400. So my x-intercept is 400, 0. So I've already got my hash marks, 1, 2, 3, 4. That's right there. Oh yeah, I wanted I mean to label these points. You don't have to do this, it's just helpful for future reference because these may be your test points for maximizing your corners, for maximizing your constraint. So, so that x-intercept is 400, 0. Now we're going to find the y-intercept. To find the y-intercept, we plug a 0 in for x, which basically zeroes out the x term, and to solve for y, we will divide by 5. This gives us 1600. So my y-intercept is 0, 1600. That means I need to go on up here 13, 14, 15, 16. And I'm right there. So my other constraint line comes in like that. And then we just have to figure out which region we're working with. Are we doing this region, or this region? Okay? And so the way we figure out which the correct region is we can use test points. If I want to test in this region, I can use any point in that region. So I always like to choose easy, simple numbers. You can use like, it gets kind of wonky if you use boundary points. So you want to actually be inside the region. So a real easy point to test here would be the order pair 1, 1. Okay? If I plug 1, 1 into either of these constraints, I'm going to get a true statement. So where I have it highlighted in yellow, that's the region I'm focusing on. So again, if I plug 1 in for my x's on my constraints, then I'm going to get a true statement, no matter on both of them. Okay? So the highlighted yellow part is my region, but what's more important is my corners. So this is one corner, this is another corner, this is a corner, this is a corner. Okay, so we have 4 corners we need to test or find the values of z for. Now we have order pairs for 3 of those, given that this one's 0, 0, and then we'll need to find the order pair for that guy. You are not expected to read it off the graph. This graph is not precise enough, given that we're counting by hundreds and all that, to read it off the graph. So what I do when I'm setting this up is I create a little chart. So I'm looking for z values at all my different order pairs. So the z value at 0, 0 is just 0, so that's probably not going to be the winner. Okay, and then another order pair, let's see if I can get that to go away, would be the 0, 12,000. Okay, so again, you're plugging these, when we're testing z values, you're plugging it into your constraint equation. So to do that, what that looks like is z equals 11 times 0 plus 4 times 1200. Okay, so which is 4 times 1200. And when you do that, you get 4800. Alright, so our next order pair that we know is 400, 0. 400, 0. That's our point down there. So in my constraint equation, if I plug 400 in for x and 0 in for y, it just zeroes out the y term, which means I'm basically taking 400 times 11. And that's going to give me 4,400. Okay? And then we have this third mystery point here. And we don't know what that is based on the graph, because the graph is too much of a sketch. What we need to do to figure out the coordinates of that point is solve the system of equations that is our constraints. Now, because those are what created our line, so where those two lines intersect will be the solution to the system of equations. So we need to solve the system of equations to determine the x and y value of that point. When I solve this system of equations, I will just work with the equals, because the less than part is all this stuff in here. The equals is what's happening on the line, which is what I'm concerned with. So I'm going to go to a clean screen to do this, so I have room to solve the system of equations, but and then we'll come back to this screen. Okay, so here are my constraint equations, except I'm just using equal signs because I'm concerned about what's happening on the line and not inside the region. All right, I'm going to solve this using the addition method, and so I'm going to get my y terms to be opposite. In order to do that, I'm going to multiply my second equation by a -4. So for the sake of showing what I'm doing, I'm just going to bring this equation over as is. And then this equation here, I'm going to take the entire thing times -4. and just bring the result over here. So I get a negative 80x minus 20y equal to negative 3200. Then I'm going to add those two together. This is going to eliminate the y term, so I have a negative 40x equal to negative 8,000. To solve that, I'm going to divide both sides by my negative 40, and that gives me x equal to 200. So that gives me the x value of the ordered pair that I'm interested in. And now what I'm going to do is take that x value and substitute it into my x in the first equation. You can substitute it into either equation. I'm just going to do the first equation because I want to. So when I do that, I get 40 times 200 plus 20y equal to 24,000. Okay, so then 40 times 200 is 8,000 plus my 20y equal to my 2400. Now I'm going to subtract my 8,000 from both sides. That gives me 16,000. And then dividing my 20 off gives me 800. Okay, so the ordered pair of that mystery point is 200, 800. So we're going to go back to the other screen and finish working out the problem. Alright, so that was 200, 800. And again, that's this mystery point right here. Now to figure out the z value for that, we need to plug the 200 into my my objective function, and then the 800 into it as for the y as well. When I do that, I get 5,400. So that's our biggest one. I do want to caution you, this point that's hard to find is not always the biggest one. You do have to check them all. Sometimes it's one of these other ones that you don't expect. Okay, so don't just assume it's going to be that point, and don't take the time to check these other points. You could probably get a little lazy about the 0, 0 point, because sending no food and no clothing is going to always help no one. Alright, now that we have all the information, we have the answer, but we need to make sure we answer the question that was asked of us. So it says, how many cartons of food and clothing should be sent? So this is our order pair. So the answer is 200 cartons of food, because X corresponds to food, and 800 cartons of clothing. Sometimes what they ask is how many people you can help, in which case the answer would be 3,400. What's the maximum number of people you can help? But here, our answer, I'll go ahead and write it in green, is the maximum number of people can be helped by sending 200 cartons of food and 800 cartons of clothing or cloths. Okay, I hope you find this helpful, and if you have any questions, just send me an email or a message and I'll try to help you out.